Yes. Hello students. So let us continue. So we were discussing about the general characteristic properties of alkali metals and alkaline earth metals. So now what are the property that we discussed? We discussed about general electronic configuration, then ionization enthalpy, hydration enthalpy, atomic and ionic size. So that we already discussed, right? And we almost there in the discussed about standard electrode potential or standard reduction potential, and we just pointed out that the factors which influence the standard reduction potential value, one is no delta HA, or otherwise you can remember delta H sublimation, delta H sublimation value. So this is the enthalpy change during the transformation of one mole of a solid into its gaseous state. So you have to provide energy, which means no this delta H sublimation enthalpy value is always no gives tend to give a positive standard reduction potential value. Positive standard reduction potential value. Remember, standard reduction potential value can be positive, it can be negative, it can be zero as well. More the positive means tendency to undergo reduction is more. More negative means tendency to undergo oxidation is more. Okay, so more the positive, more tendency to undergo reduction. Less less negative means no more negative in the sense no negative value suggests that no they have a tendency to oxidation. So that's the way you can remember. So higher the delta HA value, okay, higher the delta H sublimation value, you actually tend to get a positive standard reduction potential value. Similarly, delta H ionization enthalpy, that also no gives, you have to provide energy, same amount of energy required to remove an electron from the outermost loosely held electron no in the gaseous atom. So that is ionization enthalpy. There also no it is tend to give a positive standard reduction potential value. Positive standard reduction potential value. Then the next one is hydration enthalpy. Hydration enthalpy, delta H hydration. So remember this is actually gives more negative standard reduction potential value. Negative standard reduction potential value. So these all are enthalpy changes. So no higher the no delta H value for no this enthalpy of atomization or enthalpy of sublimation, you tend to give a positive standard reduction potential value, and higher the ionization enthalpy, you tend to get a positive standard reduction potential value. And if hydration enthalpy is higher means no that always negative, because its energy will be released. When the energy is released thermodynamically, it will be have a negative value. So delta H value will be always negative for a standard hydration enthalpy. So here you have to get you tend to get a negative standard reduction potential value if hydration enthalpy is higher. So these are the three factors which influence the standard reduction potential value. So now let us we compare the standard reduction potential value of alkali metals, and we saw lithium. Now we talking about standard reduction potential value from M plus to M. That means now what you have to understand from here, now tendency to undergo reduction from metal plus to metal is now having a value minus 3.04, which suggests you that now tendency to undergo reduction from metal plus to metal is very less. That's the way you have to understand. Okay, or now you can think the opposite, the tendency to undergo oxidation from metal to metal plus is higher. Reduction means decrease in oxidation number. Oxidation means increase in oxidation number. So look at this. And here now we selecting reduction potential as the standard. So tendency to undergo reduction from metal plus to metal is now large negative value. Suggests that now it have a very less tendency to undergo reduction or highest tendency to undergo oxidation. That why lithium having the highest oxidation potential, oxidation potential highest oxidation potential or lowest reduction potential. And from this, now one more point you can understand, this lithium is the strongest reducing agent, because now it has the highest tendency to undergo oxidation, means it is a good strongest reducing agent. That's the way how to compare. Reducing agent have a tendency to undergo oxidation, so lithium having the highest oxidation potential, which means it's the strongest reducing agent. So that's the way you can compare. Why? Now you think, now reduction potential can be positive, it can be negative, it can be zero. So look at this, it's a large negative value for a lithium. Why it's so? Even though not talking about ionization enthalpy, we know from left to right actually ionization enthalpy increases. So among alkali metals, no, ionization enthalpy is the least. And also, no, enthalpy of sublimation value, you have to provide very less energy to convert it into gaseous atom, that also, generally low. So which value which actually predominates? That's nothing but, the hydration enthalpy. Lithium having the highest hydration enthalpy among alkali metals, so no wonder they having the least or lowest reduction potential value, or they are they have a strongest tendency to undergo oxidation. So that's the way you can compare. If you talk about standard reduction potential value among alkali metals, interestingly you can observe sodium having the least value. It is now minus 2.714, minus 2.714 volt, which means if you compare among alkali metals, this is only for alkali metals, because minus value suggests they have a high tendency to oxidation, and sodium we know is highly reactive because it have a high tendency to oxidation. But you talk about reduction potential, standard reduction potential value in water, you can easily compare their tendency. If you compare other alkali metals with the lithium is the strongest reducing agent. It is having the highest oxidation potential. Sodium is the least reducing agent among this. Okay, comparing to other alkali metals, sodium having the least standard reduction potential value. So now that's the way you can compare. This value actually used to compare their oxidation reduction tendency. Now let us go to the alkaline earth metals. Among alkaline earth metals, the first point you have to come to your mind, beryllium having a standard reduction potential value 1.97, and let me write the barium, which is having the highest large negative, which is equal to minus 2.92 volt. So here two or more point there to remember. Where here we talking about reduction potential. Reduction from where to where? Reduction from metal to plus to metal, which means from oxidation state 2 to 0. Okay. So what is their tendency to undergo reduction from metal to plus to metal? Look at negative suggests they have not real tendency. If you compare other elements, not among alkaline earth metals, compare other elements, the tendency to undergo reduction from metal to plus to metal is very less. Reduction means gaining of electron. Alkali metals and alkaline earth metals have no tendency to gain electron. What's their tendency? They have tendency to lose electron. So this is what alkaline earth metals generally do. But if you talk about comparison, this is the way you can compare, where you see beryllium having the least having the least standard reduction potential value, where barium having the large negative standard reduction potential value, which means barium having a higher tendency to undergo oxidation compared to beryllium. This is now something you can compare because of the ionization enthalpy, where beryllium having the highest ionization enthalpy among the alkaline earth metals. As we move from beryllium to barium, you can see their ionization enthalpy decreases. So ionization enthalpy is one of the contributing factor. Then another important factor you have to remember, beryllium having the highest hydration enthalpy among alkali metals and alkaline earth metal, beryllium 2 plus having the highest hydration enthalpy. Hydration enthalpy, even though they have beryllium having the highest hydration enthalpy. Now if you compare lithium and beryllium, I already said lithium having the highest hydration enthalpy among alkali metals, that why it having a large negative standard reduction potential value. If you compare in that sense, now you may think beryllium having the least large negative reduction potential value, because beryllium is now having higher hydration enthalpy value compared to lithium, but it's not so, because here we're talking about first and second ionization enthalpy. Here two first and second ionization enthalpy is there, so that also contribute, where alkali metals there is only first ionization enthalpy, and here so extra factor first and second ionization enthalpy is there, enthalpy of atomization is there, so these two actually contributing to the standard reduction potential value, and beryllium having the highest ionization enthalpy among alkali metals and alkaline earth metals, because beryllium is smaller in size, so it's very difficult to remove an electron from beryllium compared to lithium. So here, if it's all depends on what's the question, because now beryllium, despite having highest in the highest hydration enthalpy, still it is not having lesser, you talk about lithium having the large negative reduction potential value, but now beryllium having touch higher standard reduction potential value. Why? Because if higher reduction potential value means ionization enthalpy and enthalpy of atomization is a contributing factor. There for beryllium it's a second group element alkaline earth metals, so its a contribution is there from first and second ionization enthalpy, that actually contribute to the standard reduction potential value, which means is beryllium not the very negative reduction potential value. It's not the beryllium, it's barium. Okay, among alkaline earth metals it's barium. Okay, one more point you can note, we expect now beryllium having the large negative reduction potential value, but it's just the opposite, beryllium having the least negative standard reduction potential value, because first and second ionization enthalpy, enthalpy of atomization or enthalpy of sublimation you can say, and these two factors actually contributing there. So it's not the hydration enthalpy is predominant here, it is the ionization enthalpy is the more predominant factor while you talk about beryllium. So that's the way you have to understand and learn. Okay, so let us move to the next characteristic property, that is flame color. Let us discuss about flame color. Flame coloration, this is something that you do in chemistry lab actually, to identify metal ions or metals. So flame coloration, each metals having a characteristic flame color. When you just heat a metal ion or metal in a flame, you will see some characteristic color. From that characteristic color you can identify which is the metal there. You may not know the metal ions, but still you can understand from the flame color. That what flame coloration is all about. So look at the color for each alkali metals and alkaline earth metals: lithium, sodium, potassium, rubidium, cesium. Among lithium it's having a color that is crimson red. It is having a color crimson red, and sodium it's yellow, and this we'll say golden yellow. It is golden yellow, and potassium having a color that is lilac in color, and this is having a color rubidium red violet, and next cesium having a color sky blue. So that is the color for lithium, sodium, potassium, rubidium, cesium. So this means they having a characteristic color. Now when you heat the flame, when you heat the metal salt in the flame. So what's the chemistry? Chemistry is nothing but when these metal ions are heated in a flame. Heat is a form of energy. So the atoms, the metal atoms present inside the salt, is getting excited. The electrons are getting excited. Electrons are getting excited to higher energy state, which means if the electrons are excited means higher excited state is unstable state, so it will come back into lower energy state with the release of energy. If the energy released is coming in the visible region, that will be colored. That why the color chemistry is all about. It's all about excitation of electron, de-excitation of electron. During the de-excitation, energy will be released. If that coming in the visible region, that will be colored. So lithium crimson red, sodium golden yellow, potassium lilac, rubidium red violet, and cesium sky blue. So all the alkali metals have a characteristic color. Now let us discuss about alkaline earth metals. Alkaline earth metals, no, you can see calcium, strontium, barium only have characteristic color. Calcium brick red, strontium that is crimson red, strontium that is crimson red, then barium that is apple green. This is a characteristic flame color for calcium brick red, strontium crimson red. Now barium is apple green. Remember beryllium. Now beryllium and magnesium do not have characteristic flame color. Why? Because they are much smaller in size compared to other alkaline earth metals, and the amount of energy, heat energy is that's getting from the flame is not sufficiently good enough to excite the electron to a higher excited state, so that it can come back and release energy. So they are the outer electrons are more tightly bound with the nucleus, so heat energy is not sufficiently good enough to excite the electron. That's why beryllium and magnesium do not have a characteristic flame color. Please note that as an important point. Let us move to the next property that we will call diagonal relationship. Diagonal relationship. What does it mean? We know if elements are arranged in a group, they have similar chemical properties. Like talking about first group, lithium, sodium, potassium. It goes on lithium, sodium, potassium, rubidium, cesium, francium. They have similar chemical property. That why they arranged in a group. They are coming in the first group. Beryllium, magnesium, calcium, strontium, barium. They have a similar property. That why they in the same group. Talking about next group, there is boron, aluminium, gallium, indium, thallium. That's another group. Then now talking about next group, carbon, silicon, germanium. So we expect an elements coming in the same group have similar chemical property, but diagonal relationship tell you that if an element the element, especially in the second period elements like lithium, beryllium, boron, have a similarity in chemical property with the element which is coming diagonal to the with respect to that metal. For example, lithium have similarity in chemical property with magnesium, where magnesium like lithium and magnesium are diagonal to each other in a standard periodic table. If you talk about modern periodic table, where lithium magnesium are now diagonal to each other. Talk about beryllium and aluminium, they also diagonal relationship, and boron and silicon also have diagonal relationship. So this is what diagonal relationship is all about. The elements in the second period elements like lithium, beryllium, boron have a characteristic similarity in chemical properties with respect to the element which is in the third period, and it should be diagonal to each other. So lithium, magnesium, similarity in chemical property. Beryllium, aluminium, similarity in chemical property, as well as boron and silicon. This is what diagonal relationship is all about. Now think why they have a similarity in chemical property. That's simply because there is four important reasons that you can remember. First one, they have similar atomic and ionic size. Similar atomic and ionic size. Similar atomic and ionic size, because we know as we move from left to right in a periodic table, atomic size decreases. As we move from top to bottom in a periodic table, atomic size increases. So going from left to right, atomic size decrease, top to bottom atomic size increase. So decrease increase, which means no, they are almost similar. Similarly, no, talking about ionization enthalpy, they have a similar ionization enthalpy. Similar ionization enthalpy. That also we know, ionization enthalpy increases from left to right, ionization enthalpy decreases from top to bottom. So increases, decreases, cancel almost, no, they are similar. Ionization enthalpy of both lithium and beryllium, lithium and magnesium are not similar. That's why they are showing a diagonal relationship. Third one, similarity in electronegativity. Similarity in electronegativity. That's another way you can think. Say electronegativities are almost similar because no, from left to right electronegativity increases, from top to bottom electronegativity decreases. So no, again no, it having a similarity. Next one you can remember. Now talk about their polarizing power. Their polarizing power is almost similar. Polarizing power is almost similar. What do you mean by polarizing power? Polarizing power means no, the ability to distort the anion. Now we know in ionic compound generally have a ionic nature, but if the charge of the cation increases, size of the cation decreases, they have more polarizing power. So if you talk about no, lithium and magnesium, they have similar size, so they are exhibiting similar polarizing power, which means no, higher the polarizing power, the covalent character between the two atoms in an ionic bond increases, because no, this cation has the power to distort the electron cloud of an anion, which means no, they increases the covalent nature, which means lithium magnesium having no similar polarizing power. So no, talking about no polarizing power, that's always for cation. So cation having a similar polarizing power. These are the main important no similarity between these two. That why no, they have the diagonal relationship. So similarity in chemical property. Now it's very important to have what are the similarity. And we said no, they have similar chemical properties. So what are they? So let us point it out one by one. First one, let us start with the diagonal relationship between no, it is lithium and magnesium. Let us start with the first one, lithium and magnesium. What is their diagonal relationship? Lithium, Li. Lithium and magnesium diagonal relationship. First one, both lithium and magnesium are harder and lighter compared to other metals. Both lithium and magnesium are harder and lighter compared to other metals. So that's the first point you can remember, both are harder and lighter compared to other elements. Both react only slowly with cold water. They react slowly with the cold water. React slowly with the cold water. We know other metals like sodium, potassium, they react vigorously with the water, but this showing that they react only slowly with the cold water. Next, their oxides and hydroxides are much less soluble in water, and the hydroxide decomposes on heating. That's another property that you can remember. The oxides and hydroxides are less soluble in water. Yes, it is soluble, but no, less soluble. Oxides and hydroxides are less soluble or less soluble. Let us know less soluble, and they decomposes on heating. For example, lithium hydroxide, when it's heated, it forms lithium oxide. Remember, oxygen is -2, lithium is +1, so exchange the valency, you will get Li2O plus it is when it's heated, water also liberated. Always write the balanced chemical equation. So 2LiOH gives Li2O plus H2O. Talk about next one, magnesium hydroxide. Magnesium hydroxide, when it is heated strongly, magnesium oxide and water will be formed. Magnesium is +2, oxygen is -2, so 2 will cancel each other, so it will be MgO. So MgO plus H2O. So here 2 MgO is required. So 2 MgO plus H2O will be the How many hydrogen here? 2 hydrogen, 2 into 2, 4 hydrogen, which means 2 more hydrogens required, right? Is it correct? 2 Mg, here 2 oxygen, here 2 oxygen, so that is not required, right? So take now MgO, let me check with MgOH twice. One magnesium, 2 oxygen here, no? 2 oxygen and 2 hydrogen, so that's enough. MgOH twice gives MgO plus H2O. So that's the way they decomposes. Lithium hydroxide decomposes to give lithium oxide and water, and magnesium oxide decomposes to give magnesium oxide and water. So the point is both are less soluble in water. We know alkali metal hydroxides are very good alkalis. So they are strong alkalis, they are highly basic in nature, which means no, that's the one unsimilarity we will see, no, because with both lithium hydroxide and magnesium hydroxide now comparatively less basic, no, where compared to others where no oxides and hydroxides are less soluble in water, where others are highly soluble. Next, both form nitrides now when combined with the nitrogen. That's also generally rare, especially among alkali metals. Lithium generally combined to form lithium nitride. When nitride is nitrogen is minus 3, lithium is plus 1, so Li3N is the formula. Lithium nitride will be formed, and 6 Li plus 3, it is N2 gives 2 Li3N. So that's the way now lithium nitride will be formed. Similarly, magnesium combining with nitrogen to form magnesium nitride. Magnesium is plus 2, nitrogen is minus 3, so minus 3, so Mg3N2, Mg3N2, magnesium nitride. So yeah, so that's the way both combine with nitrogen to form corresponding nitrides. This is not something a similarity between lithium and magnesium. Where other alkali metals okay generally do not combine with nitrogen to form nitrides, but lithium do. It's combined with the nitrogen to form corresponding nitrides. Next, their oxides, lithium oxides and magnesium oxide, do not combine with excess oxygen to form superoxides. Lithium do not form superoxides. So lithium oxides and magnesium oxide do not combine with the excess oxygen. They do not combine with excess oxygen to form superoxides. That's another similarity between lithium and magnesium that you can remember. Next, carbonates of lithium and magnesium decomposes easily on heating to form oxides and carbon dioxide. Now which means they has to be less stable, because other metal carbonates are strongly stable. That's why when they heated, they decomposes to form lithium oxides, and carbon dioxide will be released. Similarly, magnesium carbonate MgCO3, when it's heat strongly, you will get magnesium oxide plus carbon dioxide. So talk about now, if you balance this, it will be Li2O plus CO2. So that's the way both both the lithium carbonate and magnesium carbonate are easily decomposes on strong heating. Okay. Both lithium chloride and magnesium chloride, on account of their significant covalent character, they are soluble in water. So soluble in ethanol. Lithium chlorides and magnesium chloride have that covalent nature. Lithium chloride and magnesium chloride have significant covalent behavior, significant covalent nature. We expect alkali metals and alkaline earth metals to form ionic compounds, but you can see lithium and magnesium have some covalent nature. That's simply because smaller the size of the cation, higher the covalent nature. So higher the charge of the cation, higher the covalent nature. Here now you can see lithium having smaller size, very smaller size, magnesium also smaller size, and charge is higher. So these factors actually contributing to their covalent behavior. And also if they are covalent nature, means they tend to dissolve in organic solvents like ethanol. So that's another similarity in property that you can remember about lithium and magnesium. So let us rewind. the similarity in chemical property between lithium and magnesium. First one, they harder and lighter. Second point, they react slowly with water. Next point, the oxides and hydroxides are less soluble in water, which means no, the hydroxides and the hydroxides are decomposed on heating to form corresponding oxides in water. Similarly, they combine with nitrogen to form nitrides. Both lithium and magnesium form corresponding nitrides, while no, lithium oxide, magnesium oxide do not combine with excess oxygen to form superoxides. Superoxides are generally formed like potassium, rubidium, cesium, like they form superoxides, while lithium do not, like magnesium. Next, the carbonates. The carbonates has to say they are less stable because they decompose on heating easily to form corresponding oxides and carbon dioxide. And because of the high polarizing power of the cations like Li plus and Mg2 plus, they have a significant covalent character. Hence, they dissolve in organic solvent like ethanol. So that is the diagonal relationship with respect to lithium and magnesium. So next pair now also we need to learn, that is beryllium and aluminium diagonal relationship. What is the diagonal relationship between beryllium and aluminium? So let us point out one by one. Like aluminium, beryllium do not readily attacked by acids because of their presence of oxide film on the surface of the metal. Now the first point, they are not readily attacked by acids. They are not readily attacked by acids. No, something we know. No, metals generally react with hydrogen. Sorry, metal generally react with acids to form hydrogen. So that's one of the general property. But no, this is something. No, you will see similarity between beryllium and aluminium. They do not, no, easily. They do not easily attacked by an acid because they have oxide film on the surface. When no, magnesium and beryllium no exposed to the oxygen, beryllium oxide and magnesium oxide will form in their surface, that actually acting as a protective layer, which means no, that magnesium oxide and beryllium oxide layer has to remove, so that no, these metals will react. So because of the oxide film coating on the surface of the beryllium and aluminium, so they do not readily attacked by acids. Second point, beryllium aluminium are forming significant covalent behavior. Yes, AlCl3 and BeCl2 have significant covalent nature, like we saw no, in the case of lithium and beryllium. So AlCl3 and BeCl2 have significant covalent behavior. Significant covalent behavior. Which means no, lithium, aluminum chloride and beryllium chloride have covalent behavior, means they tend to dissolve in the organic solvent. So they have no, aluminum charge is +3 where beryllium is +2. So higher the charge of the cation and smaller the size of the cation, higher the polarizing power. Higher the polarizing power, higher the covalent nature. Higher the covalent nature means no, they tend to dissolve in the organic solvent like ethanol. So that's another property you can remember. Next, beryllium and aluminium dissolves in boiling alkali and liberate hydrogen to form berylates and aluminates. So the next property you can remember, both actually uh, react with sodium hydroxides in presence of water to form berylates. This is not something we will study in the coordination complex. BeOH4 and hydrogen gas will be released. So this is now we will call sodium berylates. Sodium berylates. Sodium berylates. So now, so let us balance first 2NaOH plus H2O, 2H2O. So here now Na, sodium is plus charge, beryllium is +2, hydroxide is -2. So we have to say no, whole charge, no, +2 +2, 4 -4, it has to be no 0. So sodium acting as here is a counter ion. Okay, so berylite is now actually BeOH4. BeOH4, no, that portion is berylite. So sodium berylite will be formed. Similarly, aluminium combined with NaOH. to form aluminates. That is 2NaH. To form aluminates, that is 2NaAlOH 4 times. 2NaAlOH 4 times plus hydrogen gas will be released. Okay. Both react with alkali to release hydrogen. So here we will call sodium aluminates. Sodium aluminates. So the aluminate part is actually AlOH4. Aluminium will be plus 3 charge and sodium will be plus 1. So sodium aluminate will be NaAlOH4. Okay. So beryllium and aluminium combine with the nitrogen to form corresponding nitrides. This is something now we saw in the in lithium and magnesium as well. So both beryllium, next property, both beryllium and aluminium combine with nitrogen to form beryllium nitrides, Be3N2, 3Be2, and similarly now aluminium combined with the nitrogen, sorry, N2, it should be N2, nitrogen is stable as diatomic, so AlN, aluminium nitride will be formed. So both combine with the nitrogen to form corresponding nitrides, and these nitrides react with water to yield ammonia. So both Be3N2 react with water to liberate ammonia. Both liberate ammonia gas with the corresponding hydroxide BeOH twice. Similarly, aluminium nitride you can see combine with water to form aluminium hydroxides, corresponding hydroxides, and ammonia will be released. So now always balance it here, 3BeOH twice, Be3N2, 6H2O gives Aln plus 3H2O gives AlOH thrice plus NH3. So both forms nitrides, and the nitrides when combined with water it form the combined with water to liberate ammonia. So that is the next problem that you can remember. These all are similarity between beryllium and aluminium. That's what we are talking about. Next point now. The oxides of both beryllium and aluminium show amphoteric behavior, which means they are both showing acidic and basic nature, and they react with acid and acid and alkali. Both dissolve in HCl solution as well as NaOH solution. So let us write their reaction because their oxides are amphoteric. So first react beryllium oxide with HCl to form corresponding chlorides, beryllium chloride and water. Chloride plus water. So here you can see here beryllium oxide, where HCl is an acid, which means beryllium oxide is a base here. So react with the base to form corresponding beryllium chloride. So acid base neutralization reaction. This is salt for you. Okay. Similarly beryllium oxide combined with the base. Beryllium oxide also combined with the base NaOH to form corresponding in presence of water to form corresponding berylides. Here now berylides will be formed Na2BeOH 4 times. Na2BeOH 4 times. So react with the base. Beryllium oxide react with the base to form corresponding berylides. This is again we saw berylide will be formed. BERRLAT, berylides will be formed. So this is something they're showing their amphoteric behavior. They react with both acid and base. Okay, Na which is the base, HCl is an acid. So that's a berylide formation for you. Similarly, aluminium oxide also react with HCl to form corresponding chloride AlCl3 plus water, and they react with the base as well to form corresponding aluminates. So it will be 2NaAlOH 4 times. So it will be balances aluminum chloride react with the 6HCl to form LCl3 2AlCl3 plus 3H2O. So that shows the reaction with the acid. Similarly, aluminum oxide react with the base in presence of water 3H2O. Water is there to form corresponding aluminates. So what is the point here? Both, no, it can react with both acid and base. You can see beryllium oxide react with the acid and base. Aluminum oxide react with the acid and base to form corresponding compounds. That shows their amphoteric behavior. Similarly, we discussed their oxides are amphoteric. Similarly, their hydroxides is also amphoteric. Okay, their oxides are amphoteric and also their hydroxides. For example, beryllium hydroxides, BeOH twice react with the HCl to form corresponding BeCl2 plus H2O. So here now beryllium hydroxides react with acid to form corresponding beryllium chloride. Similarly, beryllium hydroxides react with the base to form corresponding berylates. NaBeOH 4 times. Na2BeOH 4 times. Na2BeOH 4 times and similarly aluminum hydroxides react with the HCl to form corresponding aluminum chloride and water will be formed. Similarly, aluminum hydroxide react with the base like NaOH to form corresponding aluminates. NaLOH 4 times. So here now 2 moles of NaLOH 4 times will be formed. 2AlOH thrice 2NaOH to form corresponding sodium aluminate. Aluminum hydroxide similarly react with the acid to form aluminum chloride. So sodium berylate is also forms. So that is another similarity between beryllium and aluminum. Their oxides are amphoteric, their hydroxides are amphoteric as well. Then beryllium and aluminum forms carbides, and the carbides react with water to yield methane. So another property we can discuss related to their carbides. Beryllium carbides react with water to form beryllium hydroxide and methane gas will be released. So methane will be formed. Similarly, another carbide, that is Al4C3. Remember here carbon is in the -4 oxidation state. Beryllium plus 2, aluminum plus 3. So formula will be Al4C3. Aluminum carbide react with water 12H2O to form corresponding hydroxide AlOH 4 times. So sorry, AlOH thrice plus CH4. So you can see methane gas will be released. Al4C3 plus 12H2O gives 4 AlOH thrice plus 3 CH3. 3 CH4, that is methane for you. Be2C plus 4H2O gives 3 BeOH twice plus CH4. So what's the point here? Both beryllium and aluminum form carbides with charge of carbon will be -4 ion. So and these carbides react with the water to yield methane gas. Beryllium and aluminum have strong tendency to form complex. That's something you can see beryllium and magnesium have a tendency to beryllium and aluminum have a tendency to form complex. AlF6 Here 3 minus, because now aluminum is plus 3, fluorine will be minus 1, so whole charge will be minus 3. Here beryllium in plus 2 and fluorine will be is minus 1, so whole charge has to be no minus 2. Minus 2, here it will be minus 3. So they have it, and both have a tendency to strong tendency to form complex. Now you can see fluoride complex is formed by both beryllium and aluminium. Remember one point, beryllium is in the second period or aluminium is in the third period. So second period elements cannot expand their valency beyond 4. So maximum covalency of beryllium has to be 4, while aluminium has the luxury of d orbitals. Presence of d orbital means no, they can expand their valency beyond 4. So aluminium can form a complex no with having a coordinate number 6 for no aluminium. So that's another similarity and the important point you can remember. Both have a strong tendency to form complex. Next, alkyl compounds of both beryllium and aluminium are electron deficient, that they form metal carbon metal bridge bond. Next property, they have a tendency to form these alkyl compounds, and they are electron deficient in nature, and they forming a bridge bond. So let us have an example. Aluminium, triethyl aluminium, which actually existing as a dimer, triethyl aluminium, they actually form existing as a dimer. AlCH3 thrice is not stable, so they will form Al2C2H5. How many will be there? It will be 4 1, right? 1 2 3 4 5 6. Okay, let us check. You see, it's a bridge bond, so you can not in the plane. So CH2 CH3. Similarly here, you can now show one is coming towards you, one is away from you. So CH2 CH3. Similarly, you cannot here, it will be carbon bonding with another aluminium to form C2H5. Let me write C2H5 C2H5 here. This again not in the plane. They are bridge compound. You can see metal carbon metal bridge bond is forming. That's something you will see both with the beryllium and aluminium. They form alkyl compounds, metal alkyl compounds, which is now having a dimer structure with a bridge bond is forming. Now here remember they are electron deficient as well. C2H5. C2H5. Why we can say these are electron deficient compound? Because aluminium have 3 electron in the outermost shell, right? So 1, 2, 3, maximum 3 electron can be involved. Look at this, almost actually from 4 compounds. So no, aluminium doesn't have sufficient electron. So it means now we can say they are electron deficient compounds. Here carbon has to form a coordinate bond, because 2 electron forming a bond between aluminium and carbon, the both electron is coming from carbon, which means that is a coordinate bond. So 2 here, 3, 4. So that's the way valency is satisfied. Here again look at this aluminium, 1, 2, 3, maximum 3 electron is available, which means electron deficient compound, and one has to be coordinate bond. Carbon can have valency 4. So that is another point. So let us now sum up what are the points we discussed. Diagonal relationship between beryllium and aluminium. Aluminium and beryllium not readily attacked by oxygen because of their, not readily attacked by acids because of their oxide coating. Next, both aluminum chloride and beryllium chloride have no significant covalent character because of their high polarizing power of both aluminium 3 plus and Be2 plus. Next, beryllium and aluminium dissolves in alkali to form corresponding berylates and aluminates. That's something now you will see both dissolves in alkali to liberate hydrogen, and they form berylates and aluminates. And beryllium and aluminium combine with the nitrogen to form corresponding beryllium nitrides, and beryllium nitride combine with the water to form ammonia. And next point one point actually I missed, I think that is beryllium and aluminium are Lewis acids. Beryllium and aluminium chlorides are no Lewis acids. BeCl2. Look at this. This is again actually existing as a dimer. BeCl2. BeCl2. Look at this. They have a dimer structure. So BeCl2. So only one chlorine is enough because BeCl2, right? So two chlorine and one. So totally it is Be2Cl4. So again you can see chlorine chlorine is a bridge structure, and like aluminium AlCl3 also a dimer. AlCl3 also having a dimer structure. So dimer means not two units. AlCl3 two units are combined. Here also AlCl3 units, no, both combines to form a dimer like structure. So next point, both the beryllium chloride and this is beryllium chloride for a BeCl3, which is now BeCl2, which is actually existing as dimer. So two units of BeCl2 combined, and AlCl3, which is again it's again is a dimer. So now both are Lewis acids. Both are Lewis acids, and they are good. They are acting as a Friedel-Crafts catalyst. Both are Lewis acids. Both are Friedel-Crafts catalyst. What does it mean by that? Lewis acid means ability to accept a pair of electron. No, we already said it's electron division compound. So they have a tendency to accept electron pairs. So lone pair acceptor, which means no, they are acidic. So they are Lewis acids, and also Friedel-Crafts catalyst. This is something that you will learn in organic chemistry. They have a Friedel-Crafts reaction is carried out in organic compounds. They are using the catalyst like AlCl3 and sometimes BeCl2 as well. So they are Friedel-Crafts catalyst, and both forming a dimer structure in the vapor phase. Both form a dimer structure in the vapor phase. Next point, beryllium oxide and aluminium oxide are amphoteric in nature, and beryllium hydroxide and aluminium hydroxides are amphoteric in nature. And next, they combine, they form carbides. Carbides on hydrolysis gives methane gas. That's the next point. Then beryllium and aluminium have a tendency to form complex like BeF4 4 minus AlF6 3 minus. Then alkyl compounds of beryllium and aluminium are electron deficient compound with a metal carbon metal bridge one. Okay, so please go through this, read it out, and learn it. Okay, thanks for listening. Let us wind up.